Hess's law states that when reactants are converted to products, the change in enthalpy, delta H, will be the same whether the reaction takes place in a single step or in a series of steps. The keywords over here are reaction, in one single steps, or in a series of steps. To represent that graphically, we can look at this diagram over here. Let's say we have a reaction from A to convert into B. So A convert into B, this is the single step reaction, and it has the delta H value, a certain value over here. So you have another pathway of converting A into B, but the second pathway, the one you look over here, this one, A needs to be converted into X, and then from X converts into Y, and then Y, then it will be converted into B. So the one on top, the one that you are looking at here, this is the part in which the reactions are in a single step. So that is the single step, and it has the value of delta HR. And the one that you have at the bottom, the one over here, those are in a series of steps. Okay? So the value when you add up delta H1, delta H2, delta H3 will be the same as delta HR. So that is what it meant by Hess's law. The change in enthalpy will be the same whether the reaction is going to be taking place in a single step or in a series of steps. Let's have a look at another example. Let's say we have A converts into B. You have delta HR, and then A convert into M, and then M converts into N converts into P, then P converts into B. You will have another reaction, perhaps M directly to B or N directly to B without going through P. Therefore, over here you have delta H1, delta H2, delta H3, delta H4, and then here delta H5, delta H6. So the one that you are looking at right there, that is in the single step. Okay, and the value of delta HR over here, it will be the same if you're going to take the roots over here, the one in purple. If you add up H1, delta H2, delta H3, delta H4, the value will be the same as delta HR. Same goes if you want to take this roots over here. When you convert from A into M, the value of delta H1, when you add up with delta H5, it will be the same as delta HR as long as you're going to end up the same products as the single step reaction. Same goes to if you want to take the other roots right there. When you have delta H1 plus delta H2, delta H6, and you convert directly to B without going through P, the adding up of delta H1, 2, and 6 will be the same as delta HR. The enthalpy changes can be calculated by using two methods. We're going to look at the algebraic method, and second, we're going to look at the energy cycle method. In this video, we're going to look at algebraic methods in solving problems regarding to Hess's law. This is a very typical questions that you will be given in exams. You are given a set of thermochemical equations. You have number 1 here, you have number 2, and you have the third one. And the question wants you to calculate the enthalpy of formation for C₂H6 for this particular question. So let's say we're gonna be labeling this one as equation number 1. This is equation number 2. And this is thermochemical equation number 3. What we need to do over here is we need to be able to reverse certain equation, or you want to multiply that with a certain number. And why do you need to do that? The reason why you need to do that is because you want to get this target equation. This over here is what we call as your target equation. Okay? And when you look at your target equation, you have quite a lot of information that you will be needing in order for you to be able to use all the thermochemical equations over here to solve this question. Okay, so we have labeled this one as the first thermochemical equation, second, and third. What you need to do next is you need to look at your target equation and look for the species that you need to keep with you. You don't want to cancel them out, okay? So you need to have your 2C carbon solid, you need to have your 3H2 gas, and you need to have your C₂H6 gas. What you need to do now, look at your target equation, look at your carbon solid over here. Where is the position of that carbon solid? In the target equation, the carbon solid is at the reactant side. Okay, remember, this is the reactant side, and this is the product side. So that is a very basic chemical equation language that we need to know by now. 2C solids, 2 moles of carbon solid is situated at the reactant side. And how many mole? You have 2 moles of it. Okay? And by having to know that piece of information, you have to search for carbon in all of these thermochemical equations. Where can we find carbon solid? If you look at the third one, do we have carbon solid over here? No. When you look at the second one, do we have carbon solid over here? No. But when you look at the first one, you have carbon solid just right over there. Is it on the same side? When you look at your target equation, it is going to be at the reactant side. And then on your thermochemical equation, it is on the reactant side. For that, you don't have to do any reversing of equation. So you can keep thermochemical equation number 1 as it is for that part, okay? But the only thing that you need to change now, since in the thermochemical equation, you have 1 mole of carbon solid. In the target equation, you have 2 mole of carbon solid. What you need to do now is you need to multiply, okay? You need to multiply this whole thing over here with 2. So that you will get 2 mole of carbon solids over here. Okay, so means thermochemical equation, you need to times 2. Now, we have done this. Now we need to move on to hydrogen gas. We have H2 gas. How many mole? 3 mole. When you look at your thermochemical equation, hydrogen gas is on the second thermochemical equation. Is it on the reactant side? Yes, it is. Your hydrogen gas in the target equation is on the reactant side. So, when you look at the thermochemical equation here, your H2 gas is on the reactant side. So, do we need to reverse? Absolutely no. You don't have to do that because it is already on the position that we want it to be for the target's equation. But the only thing that we need to change is the same as what happened to carbon just now. We're going to be multiplying by 3. Okay, so you're going to put brackets over here. You times 3 because you need to get this hydrogen later to have the same stoichiometric coefficient as the one that you have in the target's equation. Okay, we're done with that. Moving on to the one in the product side, we have C₂H₄ gas. When you look at the thermochemical equation, where can we find it? We can find it right over there, C₂H₄ gas. Okay, but the problem with thermochemical equation number 3 right now, it is not in the same position. Your C₂H₄ is not in the same position as what you want to have C₂H₄ in the target's equation. C₂H₄ over here is on the reactant side. C₂H₄ right there is on the product side. What do we need to do with this? You have to, this whole thing over here, okay, you have to reverse, okay? You have to reverse. This whole thing will go to the other side. That whole thing will go to the other side. And this will change sign. So what you have now is this. When you times 2 thermochemical equation number 1, you'll get 2 carbon solids plus 2 oxygen gas to make 2 mole of carbon dioxide. You're going to times 2 the whole thing. And also the delta H value of thermochemical equation number 1, you too need to times 2 that number. In the beginning, it is negative 393, but now you have times by 2. You have 2 times negative 393 kilojoule. And same goes to equation 3, but this one will be multiplied by 3. You have all the equation over here being multiplied by 3. Also, the delta H value will be multiplied by 3. And for the third thermochemical equation, you will have to reverse it. So what you have over here right now, the species you have right here, is in the beginning, they are part of the product side. And the species that you have that side for the reverse version of it, it used to be part of the reactant side. So you're just going to switch them around, okay? And when you switch the equation, your delta H value will switch sign. You have negative sign before they reverse, and after they have reversed, the negative sign changes to positive sign. So again, let's have a look at what we want to keep. We want to keep 2 carbon solid. It's right over here. You want to keep that. I'm going to circle the one that we want to keep with red. And 3 mole of hydrogen gas. Okay, so you have 3 mole of hydrogen gas. Are they on the reactant side? Yes. Okay, they are on the reactant side because they are located before the arrow. And we need to keep this C₂H₄ gas. And where can you find it? You can find it right over there. Okay, the next step we need to do is, if you are able to cancel out everything else, that means your reversing and your multiplying is correct. We're going to try to cancel out the things that we do not want to have in the target's equation. Remember, this is your target's equation. So the rest of the species, which are part of the thermochemical equations, you need to try to cancel them out. Let's see if we can cancel them out. Okay, you have 2 moles of oxygen over here. You can cancel that with, okay, so you have 2 CO. We're going to try to do CO2 first. I think that one is a bit easier. You have 2 CO2 here. You cancel that. You can cancel that out. You have 3H2O right there on the product side, and then you have 3H2O gas right over there on the reactant side. So when they are on the opposite side, they should be canceled out. Now we have 2 and 3/2 oxygen gas. So remember, these are on the same side. So you need to add them together. So when you add 2 and 3/2 together, you should be able to get 7/2 mole of oxygen. And this guy over there is on the opposite side as the one if you compare with these oxygens. For that, we can say that you can cancel that, you can cancel that. Since everything is canceled out very perfectly, very beautifully, then we can add up all of the delta H values that you have on your right-hand side of your screen. You add them up, and you would be able to get a value, something like that. Okay, you get negative 84 kilojoule per mole. Okay, you're just gonna add all those numbers up, then you get like this, and the delta HF is negative 84 kilojoule per mole. In terms of marking, so how much of mark will you be getting? Okay, you'll get 1 mark for this whole thing, 1 mark for the final answer. You get 1 mark for this correct multiplying of that equation. You get 1 mark for this, and you get 1 mark for that one. Thus, in total, you might be able to get 5 or 4 marks in total for this kind of question. Let's have a look at another example. So we're going to use the same type of strategy when you want to solve Hess's law by using algebraic method. The first thing you need to do is you need to label. So that is, this is equation number 1. This is equation number 2. And that is equation number 3. And what you have below here, what you have down there, that is your, okay, so this is your target equation. When you look at the target equation, we can see that it has 2 mole of carbon solid, 2 mole of hydrogen gas, and 1 mole of C₂H₄ gas, which is your ethane. The question wants you to calculate, okay, you need to calculate the enthalpy change for between carbon, hydrogen to form the ethane. We have the 3 thermochemical equations, so we have to look for the things that we need to have inside your target's equation. In your target's equation, you have carbon solids, and where can you find it? Carbon solids is right over there, okay? Right in the thermochemical equation number 1. Is it on the reactant side or product side? So that is, okay, so that is your reactant side. And then you have your product side. And when you look at your target's equation, the 2 mole of carbon solids situated on the reactant side, and on the thermochemical equation number 1, carbon solid is also situated on the reactant side. Therefore, we don't have to reverse, but you have 2 mole over here. You have 2 mole. And this you have to times, okay, you have to times 2. When you look at the next reactant, which is H2 gas, that one is on the reactant side, and you have H2 gas on the second thermochemical equation. This one is also on the reactant side, so you don't have to reverse. You do not have to reverse. But what you need to do is, since it has 2 mole over there, you have to times the whole thing by 2. And finally, the product C₂H₄ is obviously on the product side for the target's equation, but on the thermochemical equation, C₂H₄ gas is on the reactant side. For that, we need to reverse the whole thing over here. Okay, so that will move to here, and those 2 will move to the reactant side, and the value of that will be plus 2490 kilojoule. So what we're going to have is something like this. You have equation number 1 multiplied by 2. So you have this equation. You have thermochemical equation 2 multiplied by 2. You have the new thermochemical equation. And we have reverse thermochemical equation number 3. Then you have something like this. And right now, I want to mark the thing that I want to keep for my target's equation. So in my target equation, I need to have this. So I'm going to put that circle there. I need to have 2 moles of H2 as well. So that one also I need to keep. And C₂H₄ gas, I need to keep that as well. So that one is right over here, C₂H₄ gas. I'm going to keep that. And the rest of the species that I do not circle, those are the things that we need to cancel out. So if you can cancel out everything, means your reversing and multiplying process is correct. When you look at 2CF4 on the product side, you have 2CF4 over here. Okay, 2 mole, product, reactant. So you can cancel this. You can cancel that. And we have 4F2 gas, 2F2 gas, and you have 6F2 gas over here. Remember, they are on the same side. So you're going to add them together. So when you add them together, you will have the same number of F2 gas as the one that you have over here on the product side. So you're going to cancel that 6. You're going to cancel that. You're going to get 6. And 4HF, you can cancel with 4HF as well. As you can see, I am able to cancel out everything else apart from the one that I want to keep, because these are the things that we need to have in the target's equation. So you'll write your answer like this. You're going to write down your final answer. So this one will give you 1 mark. Don't forget to times 2, negative 680. So don't forget to reverse. When you reverse, the sign will change from negative to positive or from positive to negative. So you're just going to take all of this number, you crunch them inside your calculator, and you should be able to get positive 56 kilojoule per mole. Units is emphasized. So when the question wants you to find enthalpy of formation, enthalpy of combustion, enthalpy of reaction, don't forget to write the unit as kilojoule per mole. This one, you have 1 mark. Okay, you get 1 mark over here. You get 1 mark there, 1 mark again there, and another 1 mark for reversing the reaction. In the next question, this one will be slightly more complicated than the one that we have done previously. This is because, as you can see, we have more than 3 thermochemical equations that we need to work with. Before we're going to do anything else, it's better for us to number all of the thermochemical equations so that it will be easier for us to do the analysis. This one should be thermochemical equation number 1, number 2, 3, 4, and 5. Next, what we need to do is we need to write down what is the target equation. As what we have seen previously, for this question over here, it gives you the target equation right away. Same goes to the question that we've done, the second one. But for the third one over here, the question does not give you directly. You have to read the question and try to know what sort of enthalpy do we need to know for the target equation. Reading the question from the beginning till the end, we will notice that the question wants you to determine the standard enthalpy of sublimation for dinitrogen pentoxide N₂O₅. The concept of sublimation, that is the most important thing over here. We have to know what does it mean by sublimation. We know that for sublimation, that is the process of solid converts directly to gas. Now, by using the concept of sublimation in which solids converts directly to gas without going through the liquid phase, we would be able to write the target equation. Okay, so the target equation is we have N₂O₅, okay, N₂O₅. In the solid phase, so you're going to write the phase, changes directly to N₂O₅ gas. This is the target equation. By writing the correct target equation, you will get 1 mark. Now, like what we have done in the first and second examples, we have to identify the position or the location of the species that you have in your target equation in any of the thermochemical equations in the box. We have N₂O₅ solid on the reactant side. So remember, so that is on the reactant side. And we have N₂O₅ gas on the product side. It's important for you to know that. Looking at every thermochemical equation we have in the box, which one will have N₂O₅ solid? You look at number 1, look at number 2, look at number 3, number 4, and then number 5. In the fifth thermochemical equation, when you look at the end right there, we have N₂O₅ solid. So the N₂O₅ solid right there is on the reactant side. This one is on the product side, which is supposed to be on the reactant side, because in your target's equation, N₂O₅ solids is part of the reactant. What we need to do now for thermochemical equation number 5, we have to reverse this reaction. So the first thing we need to do now, we have to reverse thermochemical equation number 5 to have your N₂O₅ solids on the reactant side, same like what we have in the target's equation. Next, let's have a look at the N₂O₅ gas product. We have to locate where is N₂O₅ gas inside any of the thermochemical equations. We have 1 until 5. When you look at number 1, look at number 2, you will be able to locate N₂O₅ gas right over here. In the target's equation, N₂O₅ gas is on the product side, and in thermochemical equation number 2, N₂O₅ gas is on the product side. For this, you don't have to do anything else. You don't have to reverse it. You don't even have to multiply that with any number, because in the target's equation, your N₂O₅ gas has 1 stoichiometric coefficient. Okay, you have 1 right there. You don't have to multiply thermochemical equation number 2 with any number. You don't have to reverse it. You're just going to copy thermochemical equation number 2 as it is. For that, it will look like this. So for equation number 2, nothing will be done, no alteration whatsoever, because the N₂O₅ gas is on the same side as the one in the target's equation, and it has the same number of mole. We have another 3 over here, and what we need to do for the other 3. And this is what's interesting now. Up until to this point, we have done for thermochemical equation number 5, when you want to locate the position of N₂O₅ solid, and also for thermochemical equation number 2, when you wanted to locate the position or where is N₂O₅ gas located. We have another 3 thermochemical equations we haven't looked at yet. And what's gonna happen now will be slightly different from what we have done in number 1, example number 1, and example number 2 in this video. I want you to observe closely because this one is very important. Before we're going to look at the other 3 thermochemical equations, if we go back over here, we can say that thermochemical equation number 2 and number 5, we are done with those 2 thermochemical equations. To make your life so much easier, it's better for you to try to cancel out the whole thing here, because we do not want to deal with that. We have done with this. Now we are left with number 1, 3, and 4. And what happens to those thermochemical equations? This is what I'm going to explain to you now. So what we need to do now, we're going to try to cancel out, okay? It sounds quite weird because we haven't worked with the whole thermochemical equations yet, but we're going to try to cancel out the thing. Of course, we're going to keep N₂O₅ solid, so we're going to keep that one, and we're going to keep N₂O₅ gas, we're going to keep that one, and we're going to try to cancel out the one that we do not want to keep. We can cancel out N₂O₅ gas. Can we cancel that out? No. Can we cancel out 2N₂O₅? No. At this point, we cannot cancel out anything. This is when you need to use whatever you have over here and try to compare with what you have remaining in there to try to cancel out things. Okay? So what we need to do now, if I'm going to open up the black box right there, what I will do is I'm going to rewrite thermochemical equation number 4 without doing anything to the thermochemical equation. When you look at thermochemical equation number 4, you have NO gas plus NO2 gas to make N₂O₅ gas. NO gas, NO2 gas to make N₂O₅ gas. When I write this down, I will notice that I can cancel this with this because the N₂O₅ gas on the reverse number 5 here is on the reactant side, and the N₂O₅ gas on the fourth thermochemical equation is on the product side. So let's have that canceled. So you can cancel that, and I can cancel that. Can we cancel anything else? I have NO2 gas over here. Do we have any NO2 gas on the other side? No. I have NO gas right over here. Do we have NO gas on the other side? No. Including oxygen gas. When you look at that, you will have the idea that these two will add up because they are on the same side, and these two will add up because they are on the same side. Now, let's have a look at the next hidden box. When I open up this box, we will see that what I've done over here, I multiply thermochemical equation number 1 with 2. Okay, with number 2. Why? When I look at thermochemical equation number 1, when I times 2 here, I should be able to get 2 N₂O₅, 4 N2 gas. So this is what I've got. I have 2 N₂O₅ and 4 NO2 gas. At this point, if I want to compare this thermochemical equation, the one that I have multiplied by 2, with the rest of those on top, we should be able to notice we can cancel out 2 N₂O₅ and 2 N₂O₅ gas. We can cancel that out. And can we cancel out 4 NO2? Look, we have NO2 gas and O2 gas. Remember, this two over here, they will add up together because they are on the same side. So this 1 plus 1 is 2. So when you cancel that out 2, you cancel this, then you get 2 NO2 right there. Can we cancel out NO gas? NO gas, not yet. So this is when you're going to get the last thermochemical equation to come in. Opening up this, you will realize that you will need to reverse thermochemical equation number 3. When you look at thermochemical equation number 3, if I have that reversed, okay, if I have this reversed, you will have that in this form. 2 NO2 gas to make 2 NO gas plus O2 gas. So when I compare that with the rest of the thing over here, we can cancel out oxygen gas because that one is on the product side with the oxygen on the reactant side. We have 2 NO2 gas right over here on the reactant side, and we can cancel that out totally over there, okay, because that one is on the product side. And lastly, we can cancel out, remember, because those two are on the same side, so they can add up with one another, making 2 NO gas and you can cancel 2 NO gas right there. When everything is canceled out beautifully, that means your number that you have over here are, when everything can be canceled out beautifully, that means we can take all of those numbers here, you add them up together, and you should be able to get the value of this whole thing. Okay, you can get all the value of this whole thing right there. So if I'm going to take that sublimation for N₂O₅ solid, what you have here, negative 22.2. So you have negative 22.2, negative 112.5, negative 112.5, negative 89.8, negative 89.8, and we have 2 times 57.2 plus 2 times 57.2 and plus 114.2 plus 114.2, and therefore the enthalpy of sublimation should be 4.1 kilojoule per mole. You'll get 1 mark for here, 1 mark for that one, and you'll get, I'm going to use a different color. You'll get 1 mark for this, 1 mark for this 2, 1 mark for that, and 1 mark for that one. In the next example that we're going to look at now, this one is a little bit higher order thinking skills, because you need to be able to produce the thermochemical equations yourself. The question gives you the information about the enthalpy of combustion for carbon, hydrogen, and methane gas. Given to you here is the enthalpy of combustion for all of these. And the question wants you to find the enthalpy of formation of methane. The first thing you need to do now is to find out what is the target equation. The question tells you that you need to find out the enthalpy of formation for methane. If we go back to the enthalpy of formation definition, it says that's the heat change when 1 mole of compound. So in this case, your compound will be the methane. So we're going to write that right here. So 1 mole of methane. 1 mole of methane is formed, okay, from its elements under stated condition. So inside the compound methane, you have elements of carbon and hydrogen. Under stated condition, under, room temperature and at 1 atmospheric pressure, carbon will exist as solid, like this, and hydrogen will exist in the form of diatomic gas, H2 gas. These are the elements, okay? The elements that you have inside there. Is this balanced? Not yet. You have 1 mole of carbon on the reactant side. You have 1 mole of carbon on the product side, but you have 4 mole of hydrogen right here. You only have 2 mole right there. How do you solve that problem? You cannot do anything over here because we need to keep this 1 mole. Okay, remember, this part has to be must 1 mole based on the enthalpy of formation, 1 mole compound. Okay, because the question wants you to write or to find the enthalpy of formation. So what we can do now is to put 2 right there to make the thermochemical equation to be balanced. Thus, this is your target equation. We have your target equation written down. When you get the correct target equation, you will get 1 mark for that. Next, what we need to do is we need to figure out the enthalpy of combustion for all of this over here. So let's do number 1 first. Okay, we're going to do enthalpy of combustion for carbon. I'm going to use red for this one. Okay, so I'm going to use number 1, combustion of carbon. So we have equation number 1. It would be carbon solid. So based on the enthalpy of combustion, 1 mole of substance is completely burned in excess oxygen. So we need to keep your carbon solid. This is the one that is being burned. Okay, plus oxygen gas. Okay. And then for the products, you would have carbon dioxide gas, and the delta H that you have should be negative 393 kilojoule per mole. Okay, so that is the first thermochemical equation. The second one is combustion for hydrogen. I'm going to use purple. So the second one there, we're going to have 1 mole of hydrogen gas combusted in excess oxygen, like what we have been told in here. Okay, 1 mole of substance. So the substance that is being burned is hydrogen gas. So you have it there. And you will be making water. Okay, when you burn hydrogen gas, you will be making water, 1 mole. That is delta H equals to negative 286 kilojoule per mole. Okay, so when we look at here, you cannot do anything for hydrogen because that one needs to be 1 mole based on the definition of combustion. You have H2 here, H2 there. You have 1 mole of oxygen over here, but you have O2 over there. What you need to do? You're going to take 1/2. Okay, so 1/2 times O2, you get 1 mole there. So that is the balanced equation. You cannot do anything for this one because just like here and there, they have to be 1 mole based on combustion. So that needs to be 1 mole and that needs to be 1 mole as well. The third one, I'm going to do that in black. Okay, so the third thermochemical equation, we have CH4 gas, okay, combusted completely in oxygen gas to make CO2 gas plus H2O gas. So that is delta H equals to negative 890 kilojoule per mole. Okay, why do you have carbon dioxide? Because you have C there. You have carbon burning, you have carbon dioxide. Why do you have water? Because when you have H and O2, you will be producing water as well. So is that balanced? Let's have a look. You have O2, O2, you have one carbon, you have H2, you have H4, you have O right there. So how do you solve that? You cannot do anything on here, but what can you change? You can change something over there. Okay, you can change something what you have over here. Since you have 4 hydrogen, over there you have 2. So to fix that, maybe we can put 2 right there. So when you put 2 times 2, you have 4. You have 1, 2, 3, 4. This time over on your product side, you have 4 oxygen. On your reactant side, you have 2 oxygen. So how do you fix that? You're going to put 2 over here as well. So when that is solved, when you have balanced the thermochemical equation, now you're good to go. You can use the thermochemical equation to get what you need to find here, which is the enthalpy of formation of CH4. So let's have a look. So when you take the target's equation, you'll realize that, okay, we're going to do exactly what we have done for number 1, 2, and 3. This is the target's equation, okay? So what we need to do, you're going to times 2 thermochemical equation number 2. You get that, number 2, okay? Number 1 will remain the same. You will need to reverse thermochemical equation number 3. So when you reverse that, when you reverse number 3, okay, you'll get this value right over here. And when I mark the one that I want to keep in the target's equation, you're going to keep that. You're going to keep that as well. You're going to keep CH4. Okay, whereas CH4 right there. So let's try and cancel out things. Can they cancel out beautifully? You have CO2. You can cancel that out. You have 2H2O gas. You can cancel that out. You have 2O2 right there on the same side. When they add up together, you have 2O2. You have 2O2 as well. So obviously, everything else can be canceled out completely, leaving out the things that you want to keep inside your target's equation. Therefore, all of these numbers right now can be added up to get your delta H formation of your CH4. So you take this number, negative 393, plus 2 times negative 286, plus 890, and you get negative 750. In terms of marking, how do you perform? So you get 1 mark for this, you get 1 mark for that, you get 1 mark for that, 1 mark for the blue bits, and 1 mark for the green bits. And that's how you're going to solve this question.